Suppose that you're faced with a question like this on a test and you're asked to match 15 definitions to their specific terms. What is the probability that you get all of them wrong? If you're new here, I'm a certified math and physics teacher in Ontario who holds a master's degree in statistics. I'm interested in this question because as a teacher myself, we often give these types of questions, and it was surprising to me that a lot of students would get them all wrong. And I kept saying, like, this is hard to do. Like, what are the odds you get them all wrong? I mean, you have 15 of them. You're bound to get at least one right. And even if you just like randomly pick them, you're bound to get at least one right. So that's why I set out to calculate this probability. What is the probability of getting them all wrong? So that's how this whole exploration started. And I started out by drawing some tree diagrams because that's a good way to build intuition. But as you can imagine, they blow up pretty quickly because with two questions, it's pretty easy. You only have a few options. You have two options. It's either you get them both right or you get them both wrong. And same thing, if you just have one question, you're obviously going to get it right. But when you have three, well, then you have 6 options, 6 permutations, right? Permutations, you can change the order. And out of those 6 options, there's 2 options where you get them all wrong. So that would be 1/3 that you get them all wrong. And then when you have 4 options, it blows up to 24. So it's like the number of questions and then factorial. That's the exclamation marks. So 4 factorial is 24 options. And already when you're at 5 questions, 5 factorial is 120. And I tried drawing a tree diagram for that, but I soon ran out of space. So then that's when I decided to write a program to do the heavy lifting for me. I've learned to program in R during my master's in statistics, and it's far from being the best tool for the job. It's just a tool I know. And I just want you right away that the code is very far from being efficient. The for loops, I'll comment on that later. So you can run a few little for loops and create essentially all the permutations. As you can see in this table, there's 24 if you have A, B, C, and D, right? That's 4 factorial. And then you can easily convert that to Boolean values. For example, the first 6 rows with A in the first entry, then that means that A was at the right spot. A is the first entry in my example, so then all of these should have a 1. And so on. When it's not A, then all the rest should have zeros. So you can convert these to Boolean values, 0 or 1. And then once you have 0 or 1s, you can count the number of items right per row. That's essentially the setup here. And instead of doing it manually for all values of n, so for example, that was for 4, then I could run it for 5 and crunch the numbers, and 6 and crunch the numbers. I set out to run a simulation with values up to 15. Just note that it might take a while to run the simulation depending on the computer power that you're dealing with. So n is the number of questions. So obviously if you have one question, you're bound to match it correctly. There's only one option. So there's 0 ways to get it all wrong. So the probability of getting a 0 is 0 for this one. If there's 2 questions, then you can get them wrong. There's 1 out of 2 ways. So that's 50%. And then if there's 3 questions, there's a third. The probability that you get 0, again, it's 2 out of 6. And then if you get 4 questions, it's 9 out of 24, which is 37.5%. And then with 5, you have 120 possibilities. So there's 44 out of those that are completely wrong. So that would be 36 and 2/3. And then with 6, you're already at 720 possibilities and you're still close to 36. So notice that you went from 0, a jump up to 50, 33, 37. So you're going up, down, up. And then you're kind of approaching a number around 0.3678. It seems like it's an asymptote of some sort. And a natural question that arises here is, what's the relationship between the column A and C? Well, that's obvious. It's just n factorial, right? So you take 1 and you put an exclamation mark. That's 1 times 1, which is 1. 2 times 1 is 2. 2 times 2, 3 times 2 times 1 is 6. 4 times 3 times 2 is 24. So that's just a factorial. But what is the relationship between A and B? That's a question where I still not have answered, but I have some hints as to where this relationship comes from. And we'll see that we can work with the asymptote to figure this out. Another way to think of this data is to visualize it. So on the x-axis, you have the number of items in your question on your test. So here I only have 8 because if you recall, the initial question was with 15, right? But 15 factorial is roughly 1.3 trillion. I think that's 10 to the 12. I think those are trillions. So 1.3 trillions, and my computer was going to blow up. So I decided to stop the simulation at 8. But it's fine to stop it at 8 because you can clearly see it approaches a certain value. And now what is this value? And it turns out that this is 0.3678. So I just guessed really like what natural number could this be? And I just guessed trial and error and I got on the first try. It's 1 over E. This is probably the value it's approaching. So I don't know the stats behind it too much, or the combinatorics behind it, but maybe someone can talk about it. We know that the denominator is definitely n factorial. And the numerator, I'm not sure. I'm not sure what is the relationship that we saw in the Excel sheet between n and the number of ways it can be 0. So if someone could figure that out for me, that'd be great. But what we do know is that when we take the limit as n goes to infinity of this thing, so something divided by n factorial, we get 1 over e, which is roughly 0.3678. And that's surprising in itself. No matter how many items you have, if you have 15 questions, the probability that they get all of them wrong is 36.78%, which is a lot higher than I thought initially. Like, what are the odds to get them all wrong? Like, that's hard to do statistically, even if you're just guessing. But over 1 out of 3 times, you're going to get them all wrong if you just guess, which is very high and somewhat counterintuitive. The next question that came up for me when doing this analysis was, if you are to guess randomly, how many questions can you expect to match correctly? So for example, if you have 15 of those associations, what are the odds that you get 1 correctly, 2 correctly? And on average, if you were to do this randomly over the long term, how many would you get correctly on average? And that's the concept of expected value, which is defined as the number of answers you get correctly times the probability of doing that if you were to guess, right? So if you have 1 question, your expected value is you're obviously going to get it right. If you have 2 questions, well, when you do the math, sometimes you're going to get 0 and sometimes you're going to get 1, and they both have 50% probability. So then that means when you multiply this out, you get 0.5. So to get this expected value, all we need to do is add up all the multiplications of the probability times the value to get the average number of questions answered correctly. When we crunch the numbers, we get a somewhat surprising result. The expected value, no matter how many questions we have in our associations, is always 1. So if you have 15 questions, the odds that you get, or on average, if you were to randomly guess, you'd get 1 correctly. 1 out of 15 isn't that good of a grade. And if you have 1 question and you're expected to get 1, well, 1 out of 1 is 100%. If you have 2 questions, it's 50%. 3 questions, it's 33%. So you can kind of see that we're dividing this number, the expected value, which is always 1, divided by n. So again, we can plot this pretty easily. We have on the x-axis, we have n. I'm putting x here, but really that could be n. And that's like a discrete number, right? It goes like 1, 2, 3, and so on. And then here would be your grade in percentage. So at the start, when you have 1, you're going to get 100% for sure. And then after that, you're already down at 50 and at 33 and at 25. So that's the relationships 1 over x, which is a rational function. And that's also kind of a cool mathematical results. So as a teacher, if you put a bunch of items, then you decrease the expected grade just by randomly selecting. And you're also increasing the cognitive load to students because it's kind of hard to match a bunch of items together. I would say anything more than like 6, you're challenging the cognitive load of students, and you might not be actually measuring how good they are at knowing those specific definitions and so on. I hope that you've enjoyed the video. It'd be great if someone could figure out the numerator in our infinite sequence. That'd be kind of cool to get the actual formula. And thanks for watching. And as always, thank you for doing the work.